The Anammox process is the biological oxidation of ammonium under anoxic conditions, coupled to nitrate reduction. This results in the production of dinitrogen gas. The process can be illustrated by the chemical equation of the catabolic reaction of the Anammox process. The reducing equivalents for the assimilation of inorganic carbon for biomass synthesis are produced from the oxidation of nitrite to nitrate, as described by the anabolic chemical reaction equation. The overall equation of the Anammox process can be obtained by summing up the catabolic and anabolic reactions. The Anammox process is performed by chemolithoautotrophic anaerobic bacteria. The bacteria belong to the genus Planctomycetes and are characterized by a slow growth rate. They are sensitive to several environmental conditions and compounds that can inhibit their metabolism. From a monitoring perspective, there is a need to track the kinetics of the process in lab and full-scale systems, not only to assess the process stability and follow the enrichment of the biomass, but also to avoid potential inhibition events. In the present video, the Anammox process will be assessed through the execution of a manometric test. The test is applied to estimate the maximum dinitrogen gas production rate of a sludge sample. It can be performed because the overall Anammox reaction leads to the production of dinitrogen gas. The nitrogen gas has a low solubility in water and can build up an overpressure in the headspace of a closed system. The overpressure can be used to estimate the moles of N2 gas produced from the Anammox reaction, and the rate at which the overpressure builds up will correspond to the production rate of dinitrogen gas. Knowing the production rate of dinitrogen gas, the maximum ammonium and nitrite oxidation rates can be estimated. The estimation of the rates can be performed using the stoichiometric relationships of the Anammox process. Considering that 1.02 moles of dinitrogen gas will be produced from the oxidation of 1 mole of ammonium, and that approximately 1.32 moles of nitrite are required to oxidize 1 mole of ammonium. As shown in the following video, the setup required to carry out the manometric test should have a closed and airtight reaction vessel. The vessel should be equipped with a pressure gauge or pressure meter and must have lateral openings, preferably with rubber septums to add the required substrates. One of the lateral openings can be used to install a water lock. The water lock can be installed by inserting a short tubing with a needle in the septum of one of the lateral openings, and by submerging the other end of the tubing in water. The tubing can have an airtight valve in the middle to control the flow of gas as desired. An incubator or water bath is needed to keep the temperature stable throughout the test. Magnetic stirrers are necessary to keep the sludge in suspension during the tests. However, if the sludge is granular, then it is recommended to use an orbital shaker. A thermostatic shaker can also be used to keep the sludge in suspension, while maintaining the temperature stable at the target temperature. A PC or laptop for data acquisition and record of the pressure readings is also useful. The main output of the test will be a pressure curve. The pressure curve will display the cumulative pressure in the headspace of the vessel as a function of time. This working sheet can be used as a guide and example to prepare and execute the manometric test. In the following video, the main steps for the execution of the manometric test to assess the Anammox activity will be explained. It includes the description of the apparatus, sludge preparation, preliminary activities, as well as the conduction of the manometric test, and the activities that need to be performed once the test has been completed. In this test, the gas-tight batch reactor should have the following features: a working volume of around 0.25 to 1 litre, 2 lateral openings sealed by airtight pierceable septa used for substrate injections and gas flushing or discharge, and a manometric measuring device with a resolution of 1 to 3 millibars connected to the headspace, if possible equipped with a data logger. The one used in this experiment had a resolution of 1 millibar. The reactor needs to be placed in an incubator that limits the temperature oscillations to plus or minus 0.2 degrees centigrade. Finally, a magnetic mixer or an orbital shaker is needed in order to ensure that the reactor remains well mixed during the batch test. All the working material should be placed next to your setup. The sampling cups and tubes should be clearly labelled and organised. The ammonium and the nitrite solutions need to be prepared in advance. In this example, the substrate solutions were prepared with ammonium chloride and sodium nitrite, both with a final concentration of 1 gram of nitrogen per litre. The working solutions can be placed in the water bath to ensure that their temperature is similar to the one set for the conduction of the batch test. The actual working volume of the batch reactor can be determined by filling it up with water and measuring its weight. First, the reactor needs to be fully assembled. A balance can be used to determine the weight of the empty reactor. The tare button is pressed to reset the weight to 0. Thereafter, the reactor is filled up with water up to the top. Before filling up the reactor to the top, reassemble it to recreate the actual working volume. Attention should be paid in order to remove any air bubbles entrapped during the addition of water. Then fill up the reactor to the top. The final weight in grams will correspond to the actual working volume expressed in millilitres. Write down the net working volume of the reactor. Empty the reactor. Thereafter, continue with the preparation of the test. Remember to verify that the portable probe was calibrated and the mixing system or orbital shaker, thermostat systems and pressure measuring devices are functioning properly. In this example, a 1.7 litre sludge sample was collected from an Anammox reactor. After the sludge has been collected, it may be washed and/or concentrated or diluted if applicable, as suggested in section 2.4.3.5 of the textbook. Once the sludge sample is ready to be used in the test, take a filtered sample to determine the initial conditions in terms of ammonium, nitrite and nitrate concentrations. In particular, nitrate should be present as a redox buffer in order to avoid the occurrence of any sulfate reduction process and consequent sulfide production, which might result in inhibiting effects during the creation of anoxic conditions. Use fast nitrate estimation methods, like paper detection strips, to quickly assess the presence of nitrate and nitrite. If the nitrate concentration is too low, for example lower than 50 milligrams of nitrogen per litre, then dose the required volume of nitrate solution. Mix gently with a stirring rod to homogenate the sludge sample. Then transfer a known volume, in this case 0.2 litres, into the reaction vessel. A balance can be used to know the precise volume of the mixed liquor added. It can be assumed that the density of the sludge is similar to the density of water and thus can be considered to be of about 1 gram per millilitre. Repeat until the required volume of sludge is transferred. The total volume of the closed reactor vessel should be known precisely in advance in order to calculate the headspace volume by the difference with regard to the sludge volume poured into the vessel. In this case, the total volume of the reaction vessel is 0.329 litres, and thus the headspace volume resulting after sludge addition corresponds to 0.129 litres. The headspace volume should be sufficient in order to avoid the creation of an overpressure higher than the maximum that can be recorded by the manometric device, due to the consumption of the substrates dosed for the conduction of the batch test. See section 2.4.9 for further recommendations. If, as usual, the apparatus for the manometric measurements does not have a pH control system, then a pH buffer solution, e.g. Hepes, 25 millimoles, may be dosed to the sludge sample, and the pH set to the desired volume, for example pH 7.5, according to the recommendations reported in section 2.4.3.5 of the textbook. In this example, a concentrated solution of Hepes, 2 moles, at pH 7.5 was used by dosing 2.5 millilitres to the mixed liquor in each batch reactor, in order to reach a final Hepes concentration of 25 millimoles. Once the sludge and the pH buffer have been added, the reactor can be reassembled. In order to remove the dissolved oxygen present in the liquid phase and create the anoxic conditions required, sparge nitrogen gas in the mixed liquor for 5 to 10 minutes. Also verify the stability of the pH, which might have been altered. In order to avoid excessive carbon dioxide stripping, a carbon dioxide containing gas mixture, for instance composed of 95% nitrogen gas and 5% carbon dioxide, can be used instead of nitrogen gas. Close the reactor vessel and flush the headspace for 5 to 10 minutes by connecting the nitrogen gas supply and a water lock, respectively, with needles inserted into the lateral openings. The water lock has a water column of 2 centimetres, corresponding to a relative pressure of 2 millibars. After the nitrogen gas supply has been disconnected, wait until gas bubbles stop rising in the water lock, meaning that the pressure in the headspace has been equalised to the atmospheric pressure. Place the reactor vessel in the incubator and start the shaking. Check that the sludge is well mixed without sludge stratification or dead volumes, and that the mixed liquor does not get in contact with the pressure transducer. Otherwise, increase or reduce the mixing speed, respectively. Check that the temperature of the control system is at the desired set point value. Typically, values between 30 and 35 degrees centigrade are adequate. In principle, to get a representative assessment of the kinetics, the temperature set point should be similar to the temperature observed at the plant where the biomass originates from. In this case, a temperature set point of 30 degrees centigrade was selected. Activate the pressure monitoring system and keep it working for a pre-incubation phase of approximately 1 hour. After 1 hour, verify that the temperature and mixing conditions are stable. The pre-incubation phase will create endogenous conditions and adjust the temperature of the reactor to the set point. If readily biodegradable organics are present, the pressure might not reach a constant value. Instead, it will keep on rising due to nitrate reduction by heterotrophic denitrification. Wait until the slope of the pressure curve becomes stable, meaning that the endogenous denitrification rate is constant. The nitrogen gas production rate of the endogenous processes will be constant throughout the test. To obtain the net maximum Anammox reaction kinetics, the nitrogen gas production rate of the endogenous processes will be subtracted from the nitrogen gas production rate observed after the addition of substrates. To be able to calculate the endogenous gas production rate by linear regression, activate the data logging at the start of the test and wait until enough data points are acquired. Thereafter, remove the stock solutions from the water bath and prepare to inject the solutions into the reactor. Remove any air bubbles from the syringe. Repeat the procedure for the second stock solution. Add the Anammox substrates, ammonium and nitrite, by injecting the stock solutions with a syringe through the septa of the reactor in order to achieve ammonium and nitrite concentrations in the mixed liquor between 50 and 70 milligrams of nitrogen per litre. See the recommendations in section 2.4.3.6 of the textbook for choosing the right starting nitrite concentration based on the type of Anammox process to be studied. In this example, 1 milliliter of each substrate solution was added to the reaction vessel in order to reach initial ammonium and nitrite concentrations of 50 milligrams of nitrogen per litre. The addition of the substrate solutions will decrease the headspace volume, resulting in a sudden pressure leap. This should be considered as an interference and disregarded during the data processing phase. Now the Anammox reaction has started and nitrogen gas is being produced, as shown by the progressive pressure increase recorded by the data logger. During the first 10 to 20 minutes after the substrate addition, the nitrogen gas production becomes faster and faster, and thus the slope of the pressure curve increases in time. In this so-called lag phase, several physical and biological processes happen simultaneously, such as water vapour pressure equilibrium, initial nitrogen accumulation in the liquid phase, and biomass reactivation processes, making the data analysis more complex. After this initial lag phase, the slope of the pressure curve will increase and reach a maximum value. This indicates that the Anammox reaction is proceeding stably at the maximum rate. When the nitrite concentration becomes limiting, the slope of the pressure curve will start decreasing due to a slower Anammox reaction kinetic rate. Once the nitrite is fully depleted, the pressure increase will stop and become stable with a slope similar to the one observed during the initial endogenous phase. Confirm that the mixing conditions and temperature are constant, since they could affect the pressure curve. The collected data should be sufficient to reliably estimate the nitrogen gas production rate through linear regression of the pressure curve data. Wait until sufficient data are recorded to be able to calculate the final endogenous rate by linear regression. The test can now be ended. Switch off the manometric system, stop the mixing, and check that the pH has been maintained within the desired range with a portable probe. Transfer the mixed liquor into a beaker and start mixing it. Take samples in triplicate to assess the concentrations of mixed liquor volatile suspended solids, carefully measuring the volume of each sample. Finally, at the end of the test, take a filtered sample for the determination of the ammonium, nitrite and nitrate concentrations. To analyse the data obtained from the manometric test, first estimate the concentrations of the stock solutions added to the reaction vessel, and also the time of addition and the volume of the stock solutions added. The time of addition of the ammonium and nitrite solutions should correspond to the increase in pressure recorded with the pressure meter. Using the data plotted in the pressure curve and the expression of the ideal gases law, the concentration of dinitrogen gas generated in the manometric test can be estimated. In particular, the actual volume of the headspace of the reaction vessel, volume estimated prior to the conduction of the test, and the temperature at which the test was executed should be considered. Once the dinitrogen gas has been generated, the dinitrogen gas production rates can be computed through linear regression. 3 different stages can be identified. The first stage, rate 1, is before the addition of the substrates. The second, rate 2, is after the addition of the substrates, which corresponds to the faster gas generation rate. And the last, rate 3, is after the substrates have been consumed. Thus, the maximum dinitrogen gas production rate, which corresponds to the maximum ammonium oxidation rate, FAMX, ammonium to nitrogen, can be estimated as the difference between rate 2 and the average rate of rate 1 and rate 3. The maximum specific Anammox activity can be computed, taking into account the volume of the sludge sample poured into the reaction vessel, the concentration of volatile suspended solids in the mixed liquor, and the maximum ammonium oxidation rate, FAMX, ammonium to nitrogen, using this expression. Therefore, using the data of the test, the maximum specific Anammox activity of the sludge sample is 0.010 grams of nitrogen gas per gram of mixed liquor volatile suspended solids per hour, or 0.237 grams of nitrogen gas per gram of mixed liquor volatile suspended solids per day. The stoichiometric ratios of the Anammox conversions can be estimated by computing the differences between the concentrations of ammonium, nitrite, and nitrate at the start of the test, just after the addition of the substrate solutions, and at the end of the test. Using these expressions, both the nitrite consumed per ammonium removed and the nitrate generated per ammonium oxidized can be estimated. In this example, the stoichiometric ratio of nitrite consumed per ammonium removed is 1.302 milligrams of nitrite per milligrams of ammonium, and the stoichiometric ratio of the nitrate generated per ammonium removed is 0.247 milligrams of nitrate per milligram of ammonium. These values are within typical values reported in literature for enriched Anammox cultures.